This session is on electronegativity. The first thing I should say, I have a little bit of a periodic chart here. And the first thing I want to point out is learn to use data in chemistry. The periodic chart, depending on if you buy one or get one from some company, sometimes it has lots of data around each element. And you need to learn to look at the patterns in data, because patterns are where we learn things in chemistry. And for instance, the first pattern is a result of some great simplification work by an American chemist by the name of Gilbert Lewis in the 30s. Lewis developed what's called the electron dot method, shows the valence electrons for elements. And for lithium, it is 1 electron, beryllium 2, boron 3 valence electrons. And notice the family is 3, or group 3. 1, 2, 3, 4 for carbon. 1, 2, 3, 4, 5 for nitrogen. 1, 2, 3, 4, 5, 6 for oxygen. 1, 2, 3, 4, 5, 6, 7 for fluorine. And neon, which is a noble gas, it doesn't react with anything, is 8. We could remove that. The same thing would be true for chlorine and sulfur, the same family. It would start off with sodium, 1 valence electron, magnesium 2, aluminum 3, etc. And then you can find patterns that group 1A and group 2 are metals. 3A is this boron is a metalloid. Then you go to nonmetals, carbon, nitrogen, oxygen, fluorine. These are gases. And these are solids over here. The third period, sodium, magnesium, aluminum, a metal, silicon, a metalloid, phosphorus, sulfur, nonmetals that are solids, chlorine is a gas, and of course argon's a gas. Now remember, any of these substances we can make into a solid, liquid, or a gas depending on the temperatures. We can change the states. Now, why am I talking about Lewis's electron dots when this is supposed to be on electronegativity? The answer is the dots represent the electrons that are involved with the bonding. And bonding can be interpreted and explained by electronegativity. And the electronegativity chart that we're putting up right here was developed by another great American chemist by the name of Linus Pauling in the 30s. And Linus Pauling is the only chemist only person who won independently, or individually I should say, 2 Nobel Prizes. One in chemistry and one in peace efforts. So the electronegativity is this. Definition: it's the relative ability of an atom to pull an electron pair from another atom. The relative ability. Here's hydrogen, 1 electron, and chlorine, we'll just put in another color here, 7 valence electrons. 8 electrons makes an octet of bond. Chlorine has, if you look on the chart, chlorine's electronegativity is 3.16, whereas hydrogen is only 2.20. So the pair of electrons bonding the two together is pulled more towards the chlorine side. And we say that hydrogen is therefore not positive, but partially positive. Now, don't let this symbol scare you. This is the lowercase delta, the Greek alphabet. This is delta negative. So the difference here is about 0.96 difference. The greater the electronegativity difference, the greater the move towards ionic or charged particle character. When you're in a range of the differences, the range of 0, no difference, to about 0.3, these things are not generally considered, these compounds, as nonpolar. When you get above 0.3 and up to about 0.1, 0.7, you have purely molecules that are polar molecules, covalent bonding. But this is really messy. I'm very hesitant to put these up because one at 1.8 plus, it starts becoming more and more ionic. Because aluminum chloride, for instance, is in the category of about 1.5 difference. Here's aluminum and chloride. And they have some ionic character and some molecular or covalent character. So I'd just like to say, in general, as it goes up from anything above 0, there's some polarity. And the polarity gradually becomes more ionic. For instance, if you take fluorine, which is the highest in the electronegativity scale, 3.98, and you combine that with sodium, which is only 0.90, and here's sodium and here's fluorine. The difference here is, wow, it's about, what, 3.08, much greater than this 1.8 here. And so sodium fluoride, one electron from sodium and 7 from fluorine, they're completely ionic. Sodium completely loses the electron, becomes a 1 plus ion. Fluorine becomes a 1 minus. Notice here I use the partial sign. That means partial charge. This is a complete charge, 1 plus and 1 minus. All molecules are going to be assessed using electronegativity. Oxidation numbers are going to be assessed. For instance, if you look at the familiar substance water, water is HOH. The oxygen has 6 valence electrons. Each hydrogen has 1. You have a total of, we'll put the others out here, 1, 2, 3, 4, 5, 6 plus a bond. You have electronegativity here. Oxygen is pulling electrons toward it in both sides. Now here this would be not polar, but it just so happens, and we'll just digress a minute to point out, water is actually a polar molecule because it's bent. We're going to study the geometry. We can even know this is bent if we take a balloon and rub it against our chest and hold it up onto a thin stream of water. You'll bend the stream of water because the polarity of the water, this is a partially negative end, and this is a positive end right here, is attracted to the electrostatic charge built up on the latex balloon. So electronegativity is going to be used a lot, and remember the scale that we have runs from 3.98 on down to potassium is listed as 0.82. It goes on down to cesium and francium, and we'll stop there.